Hello guys, last time we saw what the QR flyback converter is and what are its advantages. In this video, we'll design a QR flyback SMPS, and to make things more interesting, we'll design a USB Type-C charger using TI's new GaN FET technology. So let's start. In our daily lives, everything works on rechargeable batteries now, even our watches. To charge those things, we need a charger. So let's see how we can design one. We have already seen how a CCCV based battery charger works in this video. But today, we'll only focus on the power converter side. Before we move forward, this video is possible because of Texas Instruments and Simba. The Texas Instruments are pioneers of the semiconductor world. They make those tiny ICs which we see in our circuit boards. Their team has provided the hardware evaluation board to test and understand the QR flyback circuit using GaN FET. And the Simba is a power electronic simulation software with an awesome speed, accuracy, and simplicity, just like Flash. Now, let's start with the input requirements. We'll consider the input voltage range such that it can handle the AC input from 90 volts to 265 volts. Be it 110 volts or 230 volt standard supply, it should work all over the world. And it should be customizable, which can provide multiple output voltages such as 20 volts, 5 volts, 9 volts or 15 volts with 3 ampere load current from a single outlet, so that it could satisfy all types of devices. And we can achieve this by using a quasi-resonant flyback converter which must operate in discontinuous conduction mode or transition mode. Apart from the supply output, our circuit should have safety measures like input under voltage protection and output over voltage trigger. To design such a QR flyback, we are going to use a newly invented GaN FET from TI, which is LMG3624, which has a high efficiency and high power density. We already saw how great GaN FETs are in this video, in which we have compared all types of MOSFET. Please check that video as well. The interesting thing about this part is that it has an internal MOSFET driver and current sense circuit as well. Instead of just a MOSFET, it is a whole power module, which helps us to get higher efficiency from the design. And we'll see in a while how we can do that. We can use GaN FET in switching application, and it has a very low switching losses. Well, we want our system to be as efficient as possible. So to achieve that, we can use synchronous rectification. For that, we need to use a secondary MOSFET and a dedicated driver which can support QR flyback topologies. Also, to reduce the complexity on the secondary side, we can use this MOSFET on the returning path. So we are designing a USB-C communication based power supply. So we need a USB-C PD controller as well, which communicates with the load device and gets the information about required voltage and current. So based on that, we provide the output voltage. And most importantly, we'll use a QR flyback controller IC. Now let's start with the circuit design process. If we go with the manual design and calculations, then these all steps we need to follow in order to finalize the circuit. But we don't need to do the heavy lifting of complicated calculations. We have a cool calculation sheet for such designs. To do that, I'm using controller IC's design sheet and GaN FET design sheet for reference. Many of you are interested in these files. I've added the link of these documents in the description. You can check that. Using these spreadsheets, we get the calculated values of the components. Based on that, we can do the selection of such electronic components, including MOSFETs and transformer. Here, we can add all the input parameters which are required for the design. And based on that, it does the calculations which are needed to design the QR flyback circuit, including the peripheral components. Selecting a transformer is the biggest hassle over here. We need to provide particular parameters to the manufacturer and accordingly, it will design a transformer based on our requirements. And on this sheet, we can easily see what component values we need to design the circuit. This is how the whole circuit would look like. We have AC input, rectifier, filter. This is the flyback converter design. This is the auxiliary winding for the IC. This is the circuitry for feedback. This spreadsheet only helps us to design the asynchronous part of the design, but we are using synchronous rectification at the secondary. Additionally, we can also use the design sheet of LMG3624 for the secondary reference. Now, let's see how this LMG3624 GaNFET helps to increase the efficiency. It has an internal current sense capability. If you use an external current sensor of let's say 250 milliwatts, then this will have 363 milliwatt power loss. But the internal current sense will have only power loss of 17 milliwatts considering this formula, where this is the average current flowing through the sensor, this is the auxiliary supply, and this is the current sense simulation ratio. Because of this, our PCB becomes smaller and efficient. This flyback controller needs to identify the MOSFET voltage. But the only way to do this is to have some way of detection when the flyback coupled inductor or transformer has completely resetted. So for that, a bias winding is used as an ideal signal to indicate when the core has completely demagnetized. So we use such a special controller IC that senses the transformer reset status. Before jumping into the circuit design, we should do the simulation of the power converter circuit based on our requirements. For this, I'm using Simba software. It has a sleek GUI. We can integrate Python libraries, which is a very handy feature. It does the thermal analysis as well. And my favorite part is we can do the multiple simulations all together. Let's take our QR flyback SMPS. I have created multiple simulations for this flyback converter. All these values are as per our design specs except the IC. Instead of the controller IC, we have designed a closed loop PI controller to get the feel. Also, unlike other power electronic simulation softwares, we can add component parameters in the simulation as well as include thermal data. To do the original analysis, I have added the parameters of LMG3624 GaNFET on this MOSFET, which includes its VDS, gate resistance, RDS on, etc., etc., etc. Now, I'll simulate all of these circuits and check the output voltage of them similarly. We can compare the output voltages of all of these different circuits and how it behaves. This is the voltage across the MOSFET. As you can see, our design detects the first value of the VDS and turns on the MOSFET. And that's the beauty of QR flyback SMPS. Now, let's construct the hardware circuit of this power supply. While construction, we'll see how this circuit would work as well. Initially, let's see this GaN FET. It is an intelligent power module which has inbuilt FET driver, current sensor, enable signal capability, and a fault detection. It usually gives the signal when this FET goes into over temperature. It is a whole jackpot in a packet. We don't need an extra MOSFET driving circuit to control this. This is the heart of the system. This current sensor output goes to the SMPS IC, which detects this current and takes the action accordingly. Then we'll check the brain of the system, which is the PWM controller IC. Just like every application specific IC, it also has special logic to control this circuit. If you would like to know each function of this pin, then please let me know in the comment section. It is a special ASIC for QR flyback which is readily available in the market. At the output side, we'll use a synchronous rectifier which will be driven by MPS IC. And for USB communication, there is a USB-C PD controller. Well, this is how this whole circuit would look like. This is the input rectifier and filter section, which converts AC into filtered DC voltage. Then we have flyback transformer and it is connected to our GaN FET LMG3624. We have to provide an auxiliary winding for the PWM IC as well. This is the PWM IC and its peripheral components. On the secondary side, we have synchronous rectifier and a controller which communicates in USB-C. This is the feedback loop with an optocoupler. This part gives the feedback to the controller IC, and based on that, it provides the gate signal to a GaN FET and it switches accordingly. So overall, this is how this SMPS circuit would look like. Well, we understood how to design this circuit and how it works. Now let's see its actual version. There is no satisfaction of a design until and unless we test it in real world. So as per this design, I already have an evaluation board of QR Flyback SMPS using LMG3624 EVM from TI. This is the input filter section. This is the flyback transformer, the optocoupler. These are the output capacitors, and on the bottom side of the PCB, we have main parts of the circuit, which is rectifier, PWM IC, GaN FET, secondary side section, and its peripheral components. Now we have the evaluation board, which provides USB-C output. So we know it can give multiple outputs such as 5 volts, 9 volts, 15 volts or 20 volts. Well, I don't have the USB PD tester right now. So this directly gives the 5 volts output without any USB PD tester or any USB PD communication. Well, for now, we'll just test it out how much output voltage it gives, how much current it gives, and here we are also checking the drain to source voltage of this MOSFET. And here we are measuring the drain to source voltage across the GaN FET. As you can see, I've connected the AC input over here. Right now, I don't have any liberty to change the input voltage from 90 volts to 265 volts. So for now, I'm just testing it at 230 volts AC. And at the output side, I have connected an electronic load, which is a constant resistance load. I will change the resistance of this load, and accordingly, we'll see how this MOSFET behaves by checking its drain to source voltage. Now I've turned on the system. As you can see, there is some drain to source voltage across the GaN FET. If you see this voltage output, it is around 4.98 volts. It is taking around 2.3 amperes current. And now if you check the drain to source voltage graph, it looks like this. So this controller checks the deepest valley and accordingly it switches the MOSFET. For now I can test it with only 5 volts. Now if I change the resistance, you can see in the background the drain to source voltage changes accordingly. Well, that's how we can design a GaNFET based QR flyback converter. Alright, so let's talk about this TI's new GaNFET technology. Today we have Alex from TI's GaNFET team who is working from Dallas, Texas. And hi Alex, please introduce yourself to our audience.
Thanks, Parag. Hey everybody, my name is Alex Z. I'm one of the managers in the GaN product line at Texas Instruments. I've been with TI about 7 years, and I moved from a different team inside of TI to GaN about 2.5 years ago to help with the GaN adoption in the industry and help promote the technology.
All right, great. So today we'll talk about this new part which we are talking or we have just used in our design. And I actually have few questions about it. So can we discuss all about that? Is that fine for you?
Of course.
Yes. So, can you tell me one thing? So, you have already designed so many AC to DC converters and flyback converters, right? So, from your point of view or from your knowledge, uh, can you tell me which are the real world usage of such AC to DC flybacks?
Of course. I mean, generically, you can say anything that plugs into a wall is going to almost always have some kind of AC to DC conversion. I think the place where, at least from the GaN technology, you'll often see it being used in an AC-DC converter is like phone chargers or other kind of small power supplies where you want to power electronics and you want it to be small and light to go in your backpack. But there are other places that we're seeing it being used now. Like I said, anything that's plugging into your wall is going to need AC-DC. So the places like refrigerators, you make a Wi-Fi enabled refrigerator with a cool smart screen. Well, now you're going to need a power supply in there to power that smart screen. Same thing goes for if you have like a smart toaster. I was looking at buying a smart toaster the other day. And that obviously now comes from being an AC plug that it was a dumb toaster to having some kind of AC-DC power supply. And that always scales to, even if you think about larger power supplies, you might even have smaller power supplies within them. One example is if you have a large server power supply that's capable of operating at like 4 kilowatts, what if you're not turning it on? It needs some way to be powered up and turn on that power circuitry. So you might even have a smaller 40-watt AC-DC power supply inside your larger 4 kilowatt AC-DC power supply. So there's a lot of little interesting places like there where you may not think of these power technologies being leveraged.
So you're saying that we can see these power supplies everywhere in our daily lives, right?
Yeah, AC/DC, they're over your head in your light bulb. When you move to an LED light bulb, they're going to be in your little home appliances. I think the question, at least for me as one of the members of working on the GaN technology, is where does GaN fit into that? And the point of GaN is to try to make things smaller and more efficient. So a light bulb maybe is a good example where it's a thing in a tight spot where being a little bit more efficient, being a little bit smaller from a power circuitry perspective may be beneficial. Same thing goes in that like example, auxiliary power supplies and a bigger power supply or phone chargers. That's the one that you go on today, you go on Amazon, you're going to see 1,000 GaN phone chargers because it's smaller, more efficient, more powerful for what goes in your backpack.
Right, right. So let's say during designing such power supplies, what do you think? What are some of the most common mistakes that engineers or people like us do while designing?
I mean, one of the purposes of our group is to support the adoption of technology. And for GaN specifically, some things that I see people doing when they're doing their AC/DC power supplies would be like component placement. For example, when you put down a filter on your board, you think, oh, I need a filter on this connection between my controller and my gate driver, maybe. But we also need to think about where that filter placement happens. If you put it closer to your controller, well, you're going to be filtering out the signal that happens on that trace between your gate driver towards your controller. You put that filter closer to your gate driver, now that filter is going to benefit more your gate driver than the controller itself. So that's one common place that we're working, especially with a younger engineer or more or less experienced engineer, talking to them about where you're doing your component placement to filter out signals and to have the right placement of components. Another piece there might be power loop. One thing, especially, I'd say this is maybe like someone who's had 5 years of experience, they start to know what they want their power loop to look like, to look pretty from a board perspective. But that doesn't necessarily mean it's the smallest power loop that you can achieve. That power loop is your inductance that's going to impact your EMI and your overall performance. One example I can think of is our customer was using a really thick PCB, and they had their component placement on the backside of the board, so the power loop was going through the PCB back up to the FETs. We actually worked with them and found that moving that power loop being directly on the same layer, we did a mid-layer trace, and then back up through vias, back up to the main top layer. That was a smaller power loop than going all the way down through that PCB because it was a thick PCB. That is another place that I would always say people think about if you're running into any EMI, EMC issues. And then the last piece is understanding your equipment and test setup. I can think of one example. We had a customer, they were working with a short circuit protection issue where something was happening in the scale of 150 to 100 nanoseconds. They had 100 megahertz scope. That means they're measuring at about 10 nanoseconds pulses. And they're seeing in that pulse something in the 700, 800 volts with ringing that's in the nanoseconds. So you have to admit to yourself, okay, my equipment is not able to measure what I'm possibly having happen in my system. And that's the other thing, always knowing what is your test setup, what are you exactly measuring is really critical whenever you're trying to debug something and really test something's performance.
Right, right. Well, even though I have 4 or 5 years of experience and still I'm learning new things today.
Hey,
Yeah,
I
thank you
got
so
two
much for
guys, the
that.
two managers that I work on teammates with, they both have PhDs. They blow me out of the water.
Yeah, I can also sense that. And I have one more question on that. So, you see, this particular GaNFET has an internal gate driver, and to be honest, this is the first time I'm seeing such type of device which has MOSFET as well as the driver inside. What is the thought behind this? Why exactly did you do it?
Yeah, so there's kind of two perspectives there. One is that integration makes things easier. If you're, I mean, you actually have videos on it, designing a gate driver for your MOSFET or IGBT or whatever. When you have that gate driver built in and it's already kind of pre-designed for your FET, it just makes your first development easier. Now you don't have to worry about your gate drive resistance. You don't have to worry about any of that kind of stuff. Especially with GaN, GaN is a little bit more sensitive, has a little bit more sensitive gate. Now you don't have to worry about that gate threshold, something that one concern you basically eliminate as you do your design. The second piece of it is GaN is switching fast enough where the inductances of going outside the device start to matter. I think if you measure just like a TOE 247 package, going to a gate driver, you'll get like 10 nanohenries of inductance between the FET going over to a gate driver, just even if they're kind of co-located on the board. By building the FET in with the gate driver itself, you get down to like less than 4 nanohenries of gate loop inductance. So that kind of inductance reduction, especially when we're doing GaN, that's able to switch at 100 volts per nanosecond, which we have customers who are trying to take it up to multiple megahertz, 650 volt, multiple megahertz switching. Every little bit of inductance you can eliminate from the system matters. So putting them in the same package makes sense.
Yeah, it's like I don't have to worry about the gate driver again. I can just connect it to the microcontroller and it can work.
Yep.
Actually,
Yeah, I wish it was always that easy, but the whole point is that every time you add and say, okay, I'm going to put two things next to each other, you're adding extra complexity to your system.
That is a very
And
beautiful
if you're,
statement that I wish that could be true, or I wish that could be the reality.
yeah, it's
Okay.
impressive how many times that we've been working with people and there's just little things in their system you never would have watched. Something over here is running into, there's a transient on a line on the ground or something. And this part, not even related to your power converter, is what's blowing up or is what's causing some kind of feedback loop. It's really fun to be working on the debug of that. But when we look at integration, it's just about trying to make it a little bit simpler for people. And if we're already making it, technically making a better system solution, then it should be the best of both worlds.
Yeah, I mean, yes. Yeah, it's better if we first we test it on the actual system and then we will be able to say that, yeah, it's working.
Oh, one thing I see people always think about is they're always like, when they talk about GaN, they go, oh, I want to talk about the wide band gap and the mobility channel performance and all these like parameters of the wide band gap technologies and stuff. And the first thing I say to them is like, get out of that theoretical world. Let's look at some real systems because it is so easy to make the best thing theoretically on a data sheet, but then in the real world, it doesn't matter. An example I can think of is there's a silicon carbide supplier that we work with from a gate driver side. They have the best silicon carbide FETs per their data sheet, but then you look at their application notes, they recommend snubbers because their gates are sensitive.
Right.
Well, what is this? So you always have to think about the larger system when you make comparisons.
As a manufacturer, you're facing this issue. Think on the engineer's point of view. We have to take care of the driver side as well as the MOSFET side, and we have to integrate it. Like we have to make sure that the marriage is basically being flawless.
Mm-hmm. And that's one thing we try to solve. The gate driver team at TI sits on the other side of that wall. So the idea is that in theory, we should be talking to them. And then my friends that way, they do space power. And I have 2 or 3 friends on there that I have lunch with regularly. So the idea is that we're supposed to be resharing knowledge and trying to develop better products for engineers to use based on our learnings from multiple sides of it. And not just say, hey, I can make my thing better. It makes your life more difficult. Throw it over the wall. So.
Right, yes. And yes, I forgot about this. There is one more question. So I see that there is a current sensor inbuilt in the GaN FET as well. So I am an engineer and I have used the shunt based resistors, shunt based current sensors in my earlier projects and as of now. So can you tell me, yeah, apart from the power dissipation point of view, can you tell me what are the other advantages that I can basically utilize this onboard current sensor?
Yeah, so I mean, obviously, as you mentioned, when you ever have a shunt resistor, it's resistant, it's going to mean conduction losses. So what we're doing inside of our GaN is we have essentially a built-in GaN sense FET. So we have a FET that we're able to measure the current and able to emulate that towards your controller. It is fairly accurate. It's about plus or minus 5%. So if you go to our current sensing team, you can get better products, but for most flybacks, that's good enough. So it's perfect if you're doing like a basic PFC or AC/DC application as your feedback loop. We do try to scale it 1 to 1,000. So that is what we've spec this current sense for. So it should be fairly simple to what you might actually design in a real system with shunt resistors. And by putting it inside the package, again, it's a little bit about making the system more efficient, but by doing it as a sense FET within the GaN itself, you're not making whatever, it's 150 milliohm resistor there that's going to be seeing the current and causing losses. We're now able to do it in a little bit of a smarter way. I think we say that it's a 94% reduction. That's obviously using like a specific system condition, but it's a pretty large reduction in that loss that you would see compared to a shunt resistor using a current sense emulation. Some people even call it lossless current sense. Nothing is ever free or lossless, but going from something to 95% of it is pretty good.
Yes, okay. Well, today I learned a lot of things about Flyback in a search, about the GaNFET, and basically this new technology from TI. And well, thank you so much for joining with us today and talking to us with all about your knowledge and new technology. And pretty soon we'll talk again. So till then, thank you so much.
Thanks, Frog. Always enjoy your videos. See you soon.
Bye. Well, it's a wrap. If you like Simba, the simulation software for power electronics, then you can request a trial version. I've added the link in the description. The installation process is very easy and straightforward. And right beside that, there is a subscribe button. Don't forget to hit that as well. I'll see you in the next amazing video. Till then, stay hungry, stay foolish.